Depending on where you are in the course and how many times you've seen this video, this is an introduction or a refresher on the wildcard mask. I'm going to put this video in 3 different places in the course. At the beginning of the OSPF, EIGRP, and ACL sections, this gives you a good fundamental review of the wildcard mask before you hit those 3 areas, because all 3 of them use wildcard masks heavily. ACLs use them to determine what part of an address should and should not be examined for matches against the access control list itself. And we're going to do plenty of that in the ACL section. Their use in EIGRP and OSPF is a little bit different. It allows us to tie down which interfaces should and should not be enabled with the protocol in use. Now, wildcard masks are required in OSPF network statements. They're not required in EIGRP network statements, but their use is highly recommended. Now, wildcard masks, you'll usually write them out in binary and then convert them to dotted decimal, because that's the way you have to put them in at the router. Now, with some wildcard masks, you're just going to be able to look at the address and say, okay, I know what this is without writing it out. But here, wildcard masks, I call them bizarro subnet masks or inverse subnet masks, because the zeros in wildcard masks indicate to the router that this particular bit has to match. Ones are the I don't care bits. The ACL doesn't care if there's a match or not. It's the total opposite of a network mask. Now, in this example, we're not going to deal with the actual application of an ACL, but let's say that we need to write an ACL line that matches the subnet 196.17.100/24, because we want packets from that network to be able to come into an interface and we want to block everybody else. Well, we need to know how to write an ACL that allows packets in if the first 24 bits match 196.17.100 exactly and does not allow any other packets regardless of source IP address. Now, this is definitely the kind of wildcard mask you could write without writing all the binary out once you've practiced it, because you could look at this one and tell what it ought to be. But I want to show this to you because it illustrates what I'm talking about with these ones and zeros. If we need to match on 196.17.100 exactly, that means the first 24 bits of our wildcard mask will be zeros. The 4th octet's going to be all ones, I don't care. And you'll notice it is kind of inverse from the subnet mask itself of /24, because we know that's 24 ones followed by 8 zeros. But our wildcard mask for that particular subnet, it's going to be 24 zeros and then 8 ones, because the first 24 bits have to match exactly, and that is wildcard mask logic. And then you just convert it from binary to dotted decimal. And the wildcard mask is 000255. You really want to watch that on your exam, especially when you're first getting started with these, because it just looks funny. It's like you're looking at that answer in a multiple choice question and thinking, that can't be right. But with a wildcard mask, it is. You want to watch that on your practice exams and your real exams. Don't choose a network mask of 255.000 for an ACL when you mean to have a wildcard mask of 000255. Now, again, I grant you, this is an easy wildcard mask to determine without writing everything out. You're going to run into plenty of wildcard masks that aren't as obvious, that don't end at the very end of an octet. So practice this method of writing it out until you're totally comfortable with the process. The reason we use them in protocols, with EIGRP and OSPF in particular, let's look at a router with the following interfaces. 172.12.12.12/28 and then serial 172.12.12.17/28. Well, the 2 interfaces are on different subnets. And the key here is that we might want to run OSPF on one interface but not the other. And same with EIGRP. Well, using a wildcard mask makes this possible. The wildcard mask will require the first 28 bits to match 172.12.12.0, and the mask doesn't care what the last 4 bits are. So when you break that down, this is what it's going to look like on a per octet basis, and your resulting wildcard mask will be 00015. So again, it's a kind of an inverse subnet mask. Instead of the first 28 bits here being ones, for your wildcard mask, they're going to be zeros. Now, converted to dotted decimal, again, that wildcard mask will be 00015. That's all there is to it. And as with anything, practice makes perfect, so practice already. This is the kind of thing, again, when you've got 5 minutes here, 10 minutes there, even at home, even at work, if you're taking a little authorized break, of course, just get a piece of paper and just start writing some of this stuff out. If I had this interface, and I wanted to enable it with OSPF, and this one, what would the wildcard mask be? Getting a little bit of practice here and there like that really does pay off at the end of the day and at the end of your exam. So again, I'll put this in the OSPF, EIGRP, and ACL sections. If this is the first time you've seen wildcard masks, watch the video a couple times and then you'll see the examples, because we've got live labs in the OSPF, EIGRP, and ACL sections, and they all use wildcard masks. So we'll get plenty of practice in. I just want to give you an introduction and a refresher to refer to. Thanks for watching, and now let's get to work.